Hi, Core 4. Today we are going to continue with some of the learning we had yesterday, and we're going to expand on that to talk about compound interest. It's my understanding after talking with Miss Paul that a lot of you were already thinking in the world of compound interest, which is great, because that's, of course, what you want to get from a bank. You definitely don't want to get simple interest. So we will confirm a lot of your thoughts and suspicions from yesterday. But before we begin that, we're going to go back and we're going to take a look at what you were doing yesterday. Our learning target from yesterday was I will understand what simple interest is, and I will be able to graph a situation of simple interest, solve for an unknown interest or principal, and use the formula for simple interest in multiple situations. Reminding you of the formula, for simple interest, you're calculating the exact same interest amount every single solitary time. It is not different. It is always the same, because you're always going back to the original principal. That's why it's the same. In compound interest, that's completely different. But when you are calculating simple interest, you will expect the interest to be the same every single solitary time. So in the formula we have, P is the principal, R is the interest rate, and T is the time. Okay, so for this problem, we're going to use simple interest to find out how much money AJ is going to have. So AJ invested $1,425 into a savings account that pays simple interest. They pay the interest at 3.5% annually. That's every single solitary year. How much money is AJ going to have after 4 years? So our formula is our interest amount is equal to our profit times the rate times the time. Not our profit, excuse me, our principal. P, the principal amount is $1,425. The rate is 3.5, which translates to 0.035, and our time is 4. So that means our formula is the interest amount is equal to 1,425 times 0.035 times 4. When you do that, you get an interest rate of, your interest rate is equal to 199.50. But in order to find out how much money he's going to have, to find out his balance amount, you need to take the principal plus the interest earned. So the balance is going to equal the 1,425 plus $199.50. So that leaves you with a balance of $1,624.50. That's your answer. Hopefully that makes a little bit more sense today. So yesterday we practiced using that equation for simple interest, which we just did. Again, like I said before, simple interest pays the exact same amount of interest each term. Term could be anything, days, months, weeks, semi-annual, whatever it is, it's always different. It's easy to understand, it's easy to calculate. It's just not easy to make a lot of money. That's the only problem. So the normal way we calculate interest, the way banks use it, the way any type of investment firms use it, is we calculate using compound interest. So today's lesson is going to be about compound interest. So your learning target for today is that you will understand what compound interest is and be able to graph it, solve for an unknown interest or a principal, and use the formula in multiple situations. There's a very big, long problem that led up to the two graphs or the two tables that you see in front of you. I have chosen to skip the words in that problem just for clarification for you guys and to help you maybe understand what we're doing. What I want you to understand is when we start comparing things, and if we take a look at our simple interest calculation right here, what I want you to notice is that it's growing at this steady $2,500 every single month, or every single year, excuse me, every 5 years, jeepers, sorry. Now what I want you to do is I want you to take a look over here at this compound interest amount. So again, we start out at the same balance. After the first 5 years, you can see that it's grown by $2,763. which is actually more than the simple interest. But what I want you to understand is the leap right here. Do you see that the growth from year 5 to year 10, the next collective 5 years, is definitely more than $2,700? And then the next time it is more than that. So it's growing at this exponential rate every single time. And it's going to be much more at the end of 30 years than the simple interest. Compound interest is really where it's at. So how is this possible? Well, we're going to take a little bit of a look at that and really break down the equation and understand it. So when considering compound interest, I want you to think about the fact that it is non-linear. It's exponential. The interest is calculated on the principal plus the interest from the last term. So the increase is not the same each period. It's different. So again, just to restate, compound interest is calculated on all of the money in the account at specific points in time, completely different than simple interest. Each time the interest would be calculated, it's based on both the principal amount and any interest earned. So that's different than what we learned yesterday. Here is the formula. It's right here. A meaning the total amount that is in the account or that's owed or whatever is equal to the principal amount times 1 plus the principal, 1 plus the interest rate to the power of the number of periods of time. So this is exponential. So if you were thinking about a graph, obviously, if this was your graph would look like that. It would be that exponential increase. Hopefully that makes sense. And that's all because of this right here, because you are raising something to the power of. All right, let's take a look at our first problem. Shreya's grandfather invested $500 for her college tuition in a savings account when she was born. The account is going to pay 5% compound interest yearly. So on the next slide, we're going to see what that actually means. So here we go. You can see from this slide, this is the amount of money that Shreya's grandfather invested, $500. There's no interest earned on year 1. After year 1, there's $25 interest earned, making the balance $525. The next time we're calculating our interest, we get this amount of interest earned, $51.25, which makes the new balance be that amount. So what I want you to think about is there's 2 ways that you can go about doing this. This is a table format. We have an equation, which is A is equal to P times 1 plus R to the power of N. Let's figure out what this is. It is A is equal to 500 times 1 plus, what was our interest rate? It was 5%, so 0.05, and it's to the power of N. Again, we're going to continue to move through this. 500 times 1.05 to the power of N. I am really hoping that you see that you can take this as a formula, and I want you to think about it as a y is equal to this, where x is the number of years. You can put this equation into your calculator, and it's going to give you all of these balances. And then you would have to do the subtraction, right, between whatever the previous balance was and the new balance to get the total interest earned. So you do not need to fill out this right here. What I want you to concentrate on is this. Can you fill out the rest of that table for me? I will pause this and I will catch up with you in a minute. Okay, so I stopped at year 6. Hopefully your values for 3, 4, 5, and 6 match mine. You can go ahead and you can figure out what those differences are for the interest earned, but that's really not the point of this lesson. The point of this lesson is that you can use the formula. So let's practice using the formula a little bit more. Before we move on, I think I want to have a little discussion about what the graph looks like. So if you're taking a look at this total interest earned, you can see that we start here at 0. And after 1 month, we're up here at about 25. And then 2 months, we're up here at about 50 something. So you can see that it's going to exponentially increase. We have already talked about this, and that is because of this guy right there. All right, so let's put it in a word problem. So Parker invested $1,200 in a savings account. His bank pays compound interest at 2.4% annually. How much money will Parker have after 5 years? So let's write our formula down. So we know that A is going to be equal to the principal times 1 plus the rate to the number of terms. We know that our principal amount is $1,200. We know that our rate is 2.4%, which translates to 0.024. We know that our N, or our time, is going to be 5. So we're going to have the amount is going to equal $1,200 times 1 plus 0.024 to the power of 5. We will combine like terms, simplify 1.024 to the power of 5, and you get the amount of money that Parker has. Okay, so you get the amount of money that Parker has after those 5 years as $1,351.08. Please remember, this is money. You must round to decimal points. Let's do it one more time. This time, Allie invested $1,500 in a savings account, and her bank is going to pay compound interest at 4% monthly, which is a great deal. How much money is she going to have after 2 years? So we know that our equation is amount is equal to the principal times 1 plus the interest rate to the power of n being the number of terms. So P is going to be equal to 1,500. That's your principal amount. Your rate is 4%, which is 0.04. Now, your N, it's monthly and it's 2 years, so it's going to be 2 times 12, which is 24 periods. So your formula looks like this. A is equal to 1,500 times 1 plus 0.04 to the power of 24. Our amount is going to be equal to 1,500 times 1.04 to the power of 24. And your amount that Allie has is equal to $3,844.96. That's a nice amount, isn't it? Good for Allie. Okay, now it's time for something a little bit different. We're going to take a break and we're going to talk a little bit more about exponents. So taking a look at what you have in front of you, can you find the pattern used below? How many times are we multiplying 4? 1, 2, 3, 4, 5. So we have 4 5 times. Does it make sense that it's 4 5 times? So let's break this down and have a conversation about bases and exponents. So using this information, what I want you to understand is the big number is the base. The exponent is the 3. You take 5 and you use that caret that we've talked about, and you want to raise the 5 to the power of 3. So it's 5 to the power of 3, which is going to be 125. For the next one, the base is 3. The exponent now is 5, so it's flipped, but 3 to the power of 5 is going to be 243. Pause this video and do the next two. Okay, so for a C, I have a feeling that a lot of you did 2 divided by 3, which is a repeating decimal, which is never helpful. And then you raise that to the power of 5. What we want you to start to understand is we want back what we give. What does that mean? If I give you a fraction, I want a fraction back. If I give you a decimal, I want a decimal back. So what I want is 2 to the power of 5 over 3 to the power of 5. And that is 32 over 243. And I would like you to leave it like that because I do not need repeating decimals. So for D, we have 0.8 as the base. We have 3 as the exponent. 0.8 raised to the power of 3 is 0.52. Because I gave you a decimal to begin with, I want a decimal back. All right, that's it for today. So hopefully today was a little bit of a better day. I would like you to continue with your R&P with problems 19 and 23, and I will see you tomorrow.